Hello everyone. Today we are going to start section 2.3 properties of determinants, Cramer's rule. Also, we are going to learn another method of finding inverse matrix. Since this section is kind of long, I think I'm going to split it into two parts. Mostly we are going to have proofs and I'm going to show you an example of finding inverse. Okay, let's start with properties. You probably remember from previous class the property that if matches A has two same rows or columns, the determinant of such matrix, I'm going to label determinant of this matrix is going to be equal to 0. So that was just a review. We already learned this in previous section. Now, what is going to happen if matrix A has two proportional rows or columns? Well, by proportional, I mean, for example, row number 3 is equal some number k, row number 1. So, proportional. What is going to happen? Well, we know that also from previous section that if you multiply one row of the matrix by k, the determinant of that matrix is going to be, I'm going to do this multiplication. I take one row of matrix A and multiply it by k. So not the whole matrix. Maybe I should not write down it like this because it's going to be confusing when somebody just looks on screen without explanation. Imagine that we do have matrix A looking like A11 and here A and N. That's my original matrix A. And modified matrix is going to look like, I'm going to put it A with a star, is going to look like A11. But the second row I'm going to multiply by number K, A21. And all other rows are going to be like normal. So what is going to be the determinant of this matrix? Well, first, if we multiply one row by k, we know that determinant is going to just increase uh, oh, increase by k, right? Now, imagine now that my matrix B was a star. That this stuff we proved last section, right? If you multiply one row by a constant, that determinant is going to be multiplied by that constant. Now, imagine matrix B looks like this. I'm going to consider this two proportional rows. So I'm going to use row number 1, like normal row, and row number 2 is going to be proportional to row number 1. It's going to be K1, 1K, 1, 2, and so on. So row number 1 and row number 2 are going to be proportional. Here I labeled row number 3. Well, doesn't matter actually, but let's label row number 2 here. So for those who are just looking at the screen, everything is going to be clear. So what is going to happen? On one hand, it's supposed to be K determinant of kind of matrix B with the same rows, right? B with same rows. Why? Which are rows going to be same? The row number 1 and row number 2 are going to be same rows. And we do know it from this property that that determinant is going to be equal to 0. So we have kind of 0 multiplied by k, which is going to be 0. So basically, it does not matter if you do have exactly same rows or just proportional rows. The determinant is still going to be equal to 0. Same is going to work for columns. And that was like property number 1. Property number 2 is going to be a little bit longer to prove. And that's actually going to be a whole theorem and we are going to prove it like in a long way. Determinant of the product of two matrices equals the product of determinant of matrix A by determinant of matrix B. Very nice property, right? If you take a determinant of the product, that's a product of determinants. It's going to be a long, long way to prove. So I'm going to kind of underline this as our goal to prove. We are going to start a little bit away from this. And we are going to start with lemma. Lemma 1. Lemma, it's a small helping theory. So our major theorem is going to be this. It's going to help to prove that theorem. And lemma is going to be next. That determinant of elementary matrix multiplied by matrix B is going to be equal to determinant of elementary matrix by determinant of matrix B. So we are trying to say that the theorem is going to work, but we don't know like if it's going to work for any matrix A, but it's definitely going to work for elementary matrices. Why? Well, because elementary matrices are so simple, right? And we do very simple stuff on them also. So how I'm going to prove it? I'm just going to consider different elementary matrices and just check it. So basically, I'm planning to do case analysis. Okay, so how do we do case analysis? We are going to consider different elementary matrices. First one is going to be, well, let me see. First one is going to be multiplication of one row by a constant. Multiply row by a constant k. Well, I'm going to actually show example of elementary matrix, how it can look. Remember that elementary matrix is obtained from identity matrix by doing actually the same row operation. I'm going to multiply row number 2 by k. And I'm going to consider some arbitrary matrix B, which is going to consist of B11, B12, B13, B21, B31, B33, and some other terms in between. So now I'm going to kind of calculate determinant when I do this and calculate determinant when I do this. Imagine that like we first do determinant of elementary matrix. So what is going to be the determinant? I'm going to label this as E1. It's not like the size of the matrix, but it's kind of first elementary matrix. What is determinant of this matrix? Determinant of E1 is going to be just equal 1 by k by 1, right? Because it's a product of diagonal elements, a diagonal matrix, and it's going to be equal k. This determinant I'm just going to label as determinant of B. Determinant of matrix B, I'm just going to label as determinant of B. That's determinant of B. Now, what is going to be determinant of the product? We remember that multiplying matrix by elementary is kind of going to make operation which was done on elementary matrix. So determinant of E1B is going to be determinant of the matrix where you multiplied one row by k. Let me go back. What is going to happen? If you multiply one row by k, you multiply the whole determinant by k. So determinant of this matrix is going to be k determinant of B. Again, why does it happen? Because this multiplication of the matrix, you can just literally check it. Just multiply this matrix by B, and you're going to figure out that the product is going to be just row number 2 multiplied by k. So I'm going to use some blue marker right down so that if I put k over here and k over here, that's going to be E1B with k. So now what are we going to see? That actually if you multiply, if you calculate this determinant EB, you're going to have k by determinant B. And if you calculate this side, you're also going to have K by determinant of B, just because this is actually determinant of E, determinant of B. Well, we are going to write it down like this. Determinant E1 by determinant of B. So we kind of proved our first case, row multiplication. Case number 2, exchange. Well, here, guys, I don't want to write down exchange. Remember that exchange means that you move, like, for example, exchange row number 1 and row number 2, or row number 1 and row number 3, or whatever. Well, I'm just going to kind of apply it to this statement. I'm going to write down determinant of E2B. This one is exchange. We remember that we exchange rows from previous lecture that determinant changes a sign, right? So normally determinant of elementary matrix where you have 1, 1, 1, normal elementary matrix is 1, 1, 1, right? 0 here, 0 here. And so determinant of elementary matrix is equal to 1. If we exchange rows, the determinant is going to be equal to -1. And this one, determinant of B, is going to be just determinant of B. What is going to happen over here when we exchange rows? When we exchange rows in B matrix, if we multiply this elementary exchanged matrix by B, we are going to have exchange rows. And when you exchange rows, determinant changes to minus. So this one equals to negative B. This negative B happens because when you multiply E2 by B, you are going to exchange two rows. The result of multiplication is going to be matrix B with exchange rows, 1 or 3 or whatever. And when you exchange rows, the determinant changes the sign. That's what I did. On this side, that's a product of determinant of this matrix, which is going to be like exchange matrix, and matrix B, which is also going to be determinant of E2 by determinant of B. And you see that they are going to be equal just because this is -1 and kind of this one can be treated as -1 too. So we check the second one. And now the third one. For the third one, we do have what? We have operation which does not change the determinant. We multiply one row by a number and add it to another row, right? So I'm going to write down multiply row by number. I'm going to label K and add it to another row. Okay, how it's going to look? Well, first I'm going to write down what is going to be the determinant of this thing, E3B. Well, elementary matrix which is doing this operation, multiply by a number and add it to another row, does nothing. So determinant is not going to change. Now, what is going to be determinant of matrix E3, which is kind of having this operation? Well, because the same rule applies to E as to B, the determinant is going to be just like the matrix was not changed. And when it's not changed, it's just the matrix, like determinant of identity matrix, which is going to be equal to 1. So we can always multiply by 1 and then say that this is determinant of B by determinant of E3, which is equal to 1. So this 1 can be treated as E3. So we proved it. Well, you probably already guessed why I was doing that proof. I was doing that proof to eventually use the fact of kind of extending matrix A through elementary matrices, right? So what I'm going to do next? Well, I proved this little lemma, right? I'm going to put a finished sign. So this is going to be the beginning of my proof. And that was case analysis, right? I analyzed 3 cases. Now, what is going to happen if I have something like this? Determinant of E1 by E2 by E3 bunch of identity matrices and eventually determinant of B. Well, I can apply that formula and chop every time, like, or cut every time one elementary matrix. and write down that this is determinant of E1. And ideally, I'm supposed to write down the determinant of the rest. Determinant of E2 and B. And then I can apply the formula to E2 and kind of extend everything into a bunch of determinants. E1, determinant of E2, and eventually determinant of E matches. Well, which is good, right? If you have a product of lots of these elementary matrices, you can kind of apply the formula and split it into little product of determinants. Okay, we are done with lemma number one and kind of a little conclusion from that lemma number one, which is going to be also important for us. Now, guys, unfortunately, we do have lemma number two. It's not going to be as long as lemma number one, but it's still going to take some time. Lemma number two. Lemma number two is going to be much simpler. If A is invertible, guys, I'm going to label n by n, so it's square matrix. Invertible means has inverse. Then, guys, we have two arrows, arrow to the right and arrow to the left. Determinant of that matrix is not equal to 0. What does it mean, guys? Well, we know that this sign, we can read if and only if. For us, actually, it means that if A is invertible, then this one is true. Determinant is not equal to 0. And also, backward, if determinant is not equal to 0, then it's invertible. So basically, these are equivalent statements. Okay, we are going to start proving this side forward. So invertible, then determinant of A is not equal to 0. Well, if A is invertible, we remember that we can represent that matrix A in, or let's say, no, not matrix A, but let's kind of, if A is invertible, then you can bring it to reduced row echelon form, right? Remember that if A is invertible, that we can bring it to reduced row echelon form, R. I'm going to label it R. And the operations are A multiplied by E1, E2, and eventually lots of steps and EK over here. Well, if A is invertible, then you can bring it to reduced row echelon form, and that's supposed to be identity matrix, right? Well, let's calculate determinant of this R and determinant of the right side, which is going to be determinant of the product, right? Because A is invertible, determinant of this is not equal to 0. And actually, that's because it's identity matrix. It's going to be equal to 1. Determinant of all elementary matrices are not 0, just because we know that it's either -1 or 1 or k, depending on like which operation it was. Well, if this one is 0, then the left side is also supposed to be 0. So because we do have 1 over here, this must be not 0 too. Otherwise, we are going to get just 0 on the left side, this one. And we know that it's not 0, it's identity, right? So if matrix is invertible, then you can bring it to identity and means that determinant is not equal to 0. We proved the first part, this one. Invertible determinant is not equal to 0. Now, the second part. Well, the second part is kind of using the same kind of the same line. I'm just going to use a blue color, okay? I'm going to write down determinant of reduced row echelon form. Lots of determinants. I'm going to put only one, the first one, determinant of EK, and then determinant of A. What I'm given? I'm given the determinant is not equal to 0. So this one is not equal to 0. Well, all others are not equal to 0 because elementary matrices are never having determinants equals to 0. Then, if you multiply non-zero elements, then this one is not equal to 0, which means that it's supposed to be identity because there are two options for like reduced row echelon form of the matrix. Either it's identity or has a row of zeros. If it has a row of zeros, if it has row of zeros, then we remember that from previous sections that determinant of such matrix is equal to 0. Since it's not equal to 0, it does not have row of zeros, which means that it's identity. But it is not equal to 0, means it does not have row of zeros, means that it is identity. Well, which means that you can bring matrix A by elementary row operations to identity, which means that it has inverse. A go to I means has inverse. Okay, so this one was a shorter one, right? But actually, we used the very same kind of, same line. Sorry, supposed to write down this like this, and that's a proof. Okay, so we proved that it's invertible. Now, guys, I'm thinking maybe the theorem, I'm going to put it in the second part of our lecture because or maybe this part. I'm thinking like, because the second part is also going to have some other stuff. Yeah, let's actually put this like the theorem in this part of the lecture. Theorem itself. Theorem. Determinant of A multiplied by B equals determinant of A by determinant of B. So I'm going to also do case analysis. Number one, A has inverse. Well, A can have inverse or no. If A has inverse, we can represent it as the product of elementary matrices. They were actually inverses of the matrices we had like when we were kind of doing our operations, right? But they're still elementary matrices, so I'm going to write them down like this. E1, E2, and eventually the last one is identity, right? So if A has inverse, we can represent it like this because like we proved the theorem. Then what are we going to have? We're going to have determinant of A multiplied by B equals determinant of E1, ER, I, right? And well, because for elementary matrices we know everything, we are going to, oh, sorry, and there is B also. We know that we can separate them. So determinant of E1 by determinant of E2 and so on. And there is going to be determinant of B. Yeah, it looks a little bit strange. I do not calculate determinant of identity because it equals to 1. I'm just going to skip it. Now, guys, what I'm going to do, I'm going to combine these determinants back into 1. I'm going to write down that this is determinant of E1, ER. The last one here was R by determinant of B. Well, if I apply the formula, I'm going to get this, but I can apply the formula backward and get this. And this one, it's also kind of matrix A, so I'm going to write down that that's determinant of A multiplied by determinant of B. So if A has inverse, we can do all these manipulations with elementary matrices and get our formula. Now, if A does not have inverse, A have inverse. Well, what is going to happen? Well, we had a theorem that if matrix does not have inverse, the determinant is equal to 0. On the other hand, product of two matrices, B and A, I'm sorry, A and B, A and B. If A does not have inverse, the product is not going to have inverse too. Sorry. I'm going to write existence inverse, okay? Why does it happen? Well, remember we had a theorem that, like, if the product has inverse, let me write it down. AB has inverse, then A has inverse and B has inverse. And we also had the opposite theorem, like inverse theorem. If they all have inverses, then the product is going to have inverse. Well, but if A does not have inverse, means that the product is not going to have also inverse. Means that determinant of the product is going to be also 0. And what we have, determinant of the product AB is equal to 0. We can always represent it as 0 by determinant of B. We don't know if B has inverse or no, it has determinant not equal to 0, but now this 0 can be considered as determinant of A because it does not have inverse by determinant of B. And you see that the formula is still gonna work, though it's going to be formally equal to 0, but the formula is still going to work. So guys, we proved our theorem. Sorry, I'm sick a little bit. I think that's all for today, or for this first part of the lecture. Like, and I'm trying to point to lemma number 2. Like, we were using this lemma number 2, but we were using like negation of this lemma number 2. So if matrix is invertible, then determinant is not equal to 0, right? And if determinant not equal to 0, that's invertible. Means that invertible and determinant not equal to 0 are kind of equivalent statement. Means that not invertible, which is negation of this, is going to be equivalent to determinant equals to 0. I did not specify that, but actually that's the part we used over here in the second part when we were saying determinant equals to 0. Why? Because it does not have inverse. Because if it has inverse, then automatically by lemma 2, sorry, by lemma 2, if it has inverse, determinant is not equal to 0. But we already know that it does not have inverse. So it doesn't have inverse means that determinant is going to be equal to 0. You see, okay? So I think we are going to stop at this point, the first part, and maybe kind of move to the second, on the second part, prove the rest of the theorems.